This is Dr. Wood with Citadel Civil Engineering, and this is CIVL202 Statics, Learning Objective 3.2.3.2, looking at taking everything that we've learned about two-dimensional rigid body equilibrium and expanding it into 3 dimensions. As you know, today is the best day to learn statics because you're going to be using this content as you go forward in your engineering career. Right now, we're back at rigid body equilibrium, though we'll talk briefly about internal forces at the end of this video. But the basic idea is that we're going to take everything that we've done in 2 dimensions and expand it into 3 dimensions. And so with that, let's put some things on the board for our equations of equilibrium in 3D. So we'll recall from our discussion of rigid body, or actually particle equilibrium, that we learned that in order for things to not be moving, the sum of the forces have to be equal to 0. This was Newton's first law, and it turns out that that's still true. When we introduced the idea of perpendicular distances associated with rigid bodies, we introduced the idea of the sum of the moments equal to 0. And it turns out this is still true as well. The only difference now is that instead of only talking about forces in the x, in the y, and moments in the z direction, we can also talk about the particle translating along the z-axis coming out of the board and rotating around both the x and the y-axes. So if we were to do this in scalar notation, we would end up with 3 equations for sum of the forces equal to 0, just like we had for particle equilibrium. So the sum of the forces in the x direction equal to 0, and the sum of the forces in the y direction is equal to 0, and the sum of the forces in the z direction is equal to 0. Now we remember for scalar notation, we need to indicate direction with an arrow. And so we'll say there's our positive x and our positive y. And then we remember we draw the z with the little arrowhead pointing toward us coming out of the board. Now, when we were doing 2-dimensional rigid body equilibrium, we said that it also can't rotate. So our sum of the moments about the z-axis is equal to 0. But now in 3D, we're saying it can rotate, and we want to resist that rotation because nothing moves in this class, about the x and y axes as well. So sum of the moments about the x equal to 0, and sum of the moments about the y equal to 0. Now, if we were trying to indicate direction, we might be tempted to draw a bunch of curlicues, but that gets confusing in a hurry. And so often what we'll do instead for scalar notation is we'll draw an arrow indicating the direction of the axis, and we'll put 2 arrowheads on it with a crossbar. And so there's our moment about the x-axis, our moment about the y-axis, and then our moment about the z-axis. Keeping in mind, of course, that we already knew 3 of these equations from 2D, where we said the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0, and the sum of the moments about the z-axis is equal to 0. But now that we're working in 3D, we actually have 6 equations because we're saying it's not translating along any axis, and it's not rotating around any axis. And so with 6 equations of equilibrium, we should be able to solve for up to 6 unknowns. Now, in scalar notation, this is fairly helpful, but maybe those arrows get a little confusing. And so the other way that we can write this is in the Cartesian vector notation. So in this case, we would say the sum of the forces is equal to 0. Yeah, nothing moves. And so we'll say sum of the forces in the x direction, that's I, plus the sum of the forces in the y direction, that's j, plus the sum of the forces in the z direction, that's k. That's all equal to 0. This is exactly what we had for 3-dimensional particle equilibrium. Keep in mind that even though it's one line, we have to treat those I, j, and k components separately. So each one of those is its own equation. So one line, but really 3 equations. Now we can also talk about the sum of the moments. Sum of the moments equal to 0. And so with sum of the moments equal to 0, we'll say sum of the moments about the x-axis plus the sum of the moments about the y-axis plus the sum of the moments about the z-axis, all equal to 0. And so, again, one line, three equations. So either notation, we've got three equations with the ability to solve for up to three unknowns. Now, if we're going to do this, we're going to have to do free body diagrams. And so we're going to have to think through how we're going to identify 3D reactions from the supports. Now, in this case, it's exactly the same as what we had before. So supports generate reactions to resist motion. Supports generate reactions to resist motion and maintain equilibrium, which means that the more load we put on something, the higher our reactions will go. The reactions will respond to the load because what we're trying to do is maintain equilibrium, make sure these equations are all equal to 0. And so if a reaction resists translation along any axis, we'd expect that to generate a force reaction. So if the object can't move left and right, we need that force reaction left and right. So in the x direction. If it can't move up and down, if it resists motion up and down, then we need a force reaction instead of the support holding it in place. And if it can't come in the z direction, then we need a force in the z direction as well. And to resist rotation, we'd get a moment reaction. Moment reaction. So if it can't rotate around the x-axis, then we're going to have to apply a moment around the x-axis to hold it in place. If it can't rotate around the y-axis, we have to apply a moment there to rotate it around the y-axis. And if it can't rotate around the z-axis, we have to have a resisting moment around the z-axis as well to hold it in place. And so for each support, we have to go through this process and think through what directions can it move. Now, one of the misconceptions that we'll have sometimes when we're looking at these reactions is that we'll think about, well, if it moves all the way over, then it'll start to resist rotation or motion. And that may very well be true for different types of reactions. But typically what we're going to do is we're going to look at how they're resisting either translation or rotation within their normal range of motion. So if we think about the joint in my elbow, right? So I can rotate it this way, right? I can even rotate this way. That's kind of cool. And the elbow doesn't really let me rotate this direction. That's kind of the shoulder that lets me rotate it that direction. And you could say, well, cool, it resists, rotation that way. But if you stretch your arm all the way out, it's going to generate a moment when you try to stretch your arm. Well, that's breaking my elbow. I don't really want to design anything that resists rotation in that direction. And so the same thing with these joints. So when you start looking at ball joints and different things, it would have all these different resistances of translation, and it can kind of rotate freely in a ball joint as long as you're within the design range. And that's really where you want to live, is within that design range. If you need some help interpreting 3D reactions, there's a great table in your book, table 5.2 of your textbook, and I'll show you real quick. It's got a whole slew of different three-dimensional reactions. And so you can see there how it has the moment and forces and the different things going on there as we go through. And so that's a great resource for you to use as you're working on your homework and trying to interpret the different types of three-dimensional reactions you're looking at. So that's definitely an issue for us. Let's see. Go back to our PowerPoint slide. And there's one other issue we want to talk about here. Actually, two issues. One is stability. So when we look at these different situations, we might be tempted to say, okay, well, that's a journal bearing there at point A on the rightmost object. And so if I look at that uh, in my textbook here, see that right there? It looks like it'll resist both forces and moments, which to a certain extent is true. However, we don't really want to design things that way, because what's going to happen is that when you try to resist the twist, it's going to bind. And so this is something that comes into play when we talk about stability and reactions, and you'll do more of that in structural analysis in some of your later classes. But often what we'll do is we'll design a system so that other locations, other forces acting at distances resist the moment, rather than trusting the single journal bearing or whatever to resist that moment. Now, a great example of this is kitchen cabinets. I don't know if y'all, I mean, everybody's seen a kitchen cabinet. And typically, kitchen cabinets have two hinges on them, right? And the reason they have two hinges is that if you use one hinge, it'll actually resist moment, right? It doesn't really want to twist on a single hinge. But the door will bind when you do that. Instead, if we use two hinges, the two hinges can now just act basically as pin connections. And to resist the moment, you've got two forces equal in magnitude, opposite in direction, with this perpendicular distance between them. Well, that's a moment couple. That's what's resisting the moment. And so I don't know if you've ever seen a cabinet door that only had one hinge, but I imagine most of the time you see a cabinet door with only one hinge, it looks like it's a little askew, because the hinge is trying to resist moment, and it's just not great at that. It can, but it's not good at it. And so using multiple hinges so that you get only those single force reactions is a thing. Now, we're not going to do a whole lot with that in this class, but I do want you to be aware that stability and doing designs like that really matters. So like for my mechanical engineering students, you could look at a journal bearing through a drivetrain, right, for a vehicle where it is going to be rotating. And yes, the little coupling that could hold it in place could resist moment. So if you tried to twist the drivetrain, it would hold it in place. But if you try to twist that drivetrain while it's spinning, it's going to bind, and that's not what you want. So you really want to have two of those couplings so that the forces, just the translation forces, are holding it in place rather than also resisting a moment. Hopefully that makes sense to you. The last thing I want us to talk about very briefly are our internal forces. We talked about this in the previous video for 2D, and we actually mentioned all of these forces. The thing to point out here is that now we can bend an object. So if I grab my object here, not only can I bend it this way, right? I can also bend it this way. And so there's two bending moments, and then there's that torsion, the twist. So those are my moments that can develop internally. I'll still have a normal force, either in tension or compression. And now I can also have shear that acts this direction, or I can have shear that acts kind of out of plane. And so I end up with 6 internal forces potentially that I can talk about in a given beam. 1 normal force, 2 shear forces, 1 bending moment, or actually 2 bending moments, and 1 torsion moment that we'd have to deal with for our internal forces. If we wanted to calculate those internal forces, it would be the same thing. We would do our external reactions first, and then we cut the member, exposing all 6 internal forces and writing our equations of equilibrium, 6 equations of equilibrium, to solve for those 6 internal forces. I'm not going to ask you to do that in this class, especially for my civil engineers. The beautiful thing about being a civil engineer is that often you can break all of your problems down into 2D. But I did want to mention that. I look forward to doing seeing how your discussion goes on the board, as well as doing an example problem in 3D with you soon. And with that, I'll sign off.